It is a pleasure for me to introduce Sallah Eddine Boutiah from the University of Sétif in Algeria. He will speak on kernel estimates for elliptic operators with unbounded diffusion drift and potential terms. Please, Sallah.
Thank you, Abdel, for this introduction. And today I'm going to talk about some elliptic operators for elliptic height current estimate for elliptic operators with unbounded coefficients. And the main the main source of this presentation is the following paper, which is in collaboration with Abdelaziz Randi and Christian Tascelli from University of Sallah, where we have published this paper in Journal of Discrete and Continuous Dynamical System, Series A. So let's start directly by the model operator. We have an operator defined by expression 1 here, 1 plus x power alpha in the diffusion part, plus b x alpha minus 2 in the drifts, minus c x power beta, which is the potential term. C is strictly positive, and we have the following condition on alpha. Alpha is strictly bigger to 2, and beta is bigger to alpha minus 2, where b is a constant in R, and as I said, C is strictly positive. So we consider this operator in LP, and what we want to do, the first thing, we have the following two questions. The first one is to show that the ground state associated to the operator A satisfy the following upper and lower bound for X larger north. And the second question, which is the important one, is to prove that the kernel K associated to the semi-group generated by the operator A satisfy the following upper bound. So this is the two things that I will present in this talk. Before that, let's introduce some results associated to the operator A. We have proved with Federica and Randy and Christian that the realization of this operator generates a C0 semigroup in LP without any condition on P. To do that, by some transformation, we can eliminate the drift term and transform this operator to a Schrodinger type operator with a new potential, which is in the Rupert-Holder class, and do some technique to chain to get generation results. Then this semigroup is analytic, consistent, ultra-conductive, and compact. Third point is that this semigroup maps LP into space of continuous of order 1 plus V, bounded. And we have further properties, which is that the domain, the maximal domain of this operator coincides with some subloop space, which means we have characterized exactly the domain of the realization.
So can you show again the assumptions on A, alpha, and beta?
On this one?
Yep. Oh, okay. All right. Thanks.
Yeah. So in this table, I collect all the results about this kind of operator from 2007 by different authors from different universities in Italy and in Germany, where we have, for example, only the diffusion part, or the diffusion part plus the drift part, or the diffusion part plus the potential part, which is the Schrodinger type operator, or the complete operator where we have all three parts. So under condition on alpha and beta, or a condition on P, one can get this operator generates a C0 semigroup in LP with different condition on P. So the main result of this talk is the following. We take C equal to 1 just to simplify the calculation, which is work also for general C. Then under our condition on alpha and beta, and for X and Y sufficiently large, then the kernel K associated to the semigroup generated by A satisfy the following upper bound, where lambda 0 is the largest eigenvalue of the operator A, and gamma is given by the following constant, which is beta minus alpha plus 2 over beta plus alpha minus 2. So let's start by the first point, which is the ground state associated to the operator A. In the following proposition, we prove that the ground state is bounded from below and from above by this function under our condition. To do that, the proof is very technical. So we know that the ground state associated to this operator is radial, since the coefficient is of our operator is radial. Then we have a C equal lambda 0 psi. So we can use a polar coordinate and try to look for an approximation solution for ODE in one dimension. So we can use some idea from Liouville-Green approximation. To give you a sketch of proof, we consider the following function, G, which is defined by this expression, where H here is our potential divided by the coefficient of the potential, the coefficient of the drift term, which is x power beta over 1 plus x power alpha, and V lambda here, which is a function that will be chosen later on calculation. So we set a W R is given by our function G multiplied by this polynomial function, which is exactly given by expression 3 here. And what we'll do, we compute the first and the second derivative of W, which we can find formula 4 here, where G1 is given by expression 5 and the function M is given by this formula here. And on the other hand, by computing direct the second derivative of 3, one has that the second derivative can be exactly this expression. So if we compare with the 4 with this one, with this one, we can get our operator divided by 1 plus power alpha in the polar coordinates, which is exactly given by expression 6 here, where G1 is the function given before, this one, given by expression 5. And what will we do? We take V, which is a series from 1 to K, C each constant, 1 over R, this beta minus alpha over 2 plus 1, and do some calculation to simplify the function G1 and use maximum principle for some parabolic equation to get our results, which is it's very, very technical and long. So I stop here. And we have here 2 remarks. The first one, if B equal to 0, we can obtain exactly the upper and lower estimate for the Schrödinger type operator A0C in the case of alpha bigger to 2 and beta bigger to alpha minus 2. And in the general case where C, the constant C is strictly positive, we can also prove that the ground state associated to A is bounded by this function, which the only difference is C in the potential terms. Now we are interested to the second question, which is the height current estimate. We consider Hilbert's weighted Hilbert space L2 mu with weight 1 over 1 plus alpha, and we consider this function eta of x equal to 1 x power alpha b over 2 minus alpha. Just remember that b here is the coefficient of the drift term, and the multiplicative operator defined by this expression tu equal to eta u. Then the operator a, our operator, can be written in the following way, which is our multiplicative operator, the inverse of our multiplicative operator h t, where h is exactly the Schrödinger type operator with the following potential u. And as you see here, in the case where beta is directly bigger to alpha minus 2, then U is bounded from below. So now we associate to the operator H a bilinear form, which is defined by expression 9 here. It's so simple. With its domain, the H, with Hilbert space H defined by this H, capital H, or with inner product D plus U V W d mu plus the quadratic form, where D equal to minus infinity of U. Then we can easily prove that the form, the quadratic form is symmetric, continuous, closed, and quasi-accretive. Then we can associate to this quadratic form a self-adjoint operator H, denoted H mu, quasi-dissipative, defined with the domain with its domain, such that by classical result, this self-adjoint operator generates a positive and analytic semigroup in L2 mu. And then we have the following lemma, that the domain of this this self-adjoint operator coincides with this one. And we have that the relationship between the resolvent of H mu and our operator. And thanks to this, we know that the weighted operator is given by the weighted H is given by an integral kernel, and the kernel K mu satisfy this equality, where eta, as I defined before, which is 1 plus x power alpha over b power b over b over 2 alpha. And we have the following proposition, which is on diagonal kernel under our condition. Then we can easily prove that ktxx is bigger or equal to this formula. To prove this, we use semigroup law and just Holder inequality. So you can see the data is here. We use semigroup law, and then we use the Holder inequality. And we know that the norm of eta multiplied by the ground state or the eigenfunction is finite. Then we can exactly find this this bound. And now to prove the upper bound, we use the relationship between ultra contractivity and the log Sobolev inequality. We use the following lemma from Davies. I collect these two lemma in this proposition. So if we have a monotone decreasing function beta such that we have this inequality, f squared log f is bounded by this function, where h is the bilinear form. And for any f in this domain, the h, which is intersection between L1 and infinity, and the domain of the form, if we take the medium of beta epsilon, which is the coefficient of f in L2, then the operator is ultra contractive, means that is bounded from L2 to infinity. And then when we have the operator is ultra contractive, we can see from Davies that the kernel is bounded by c t over 2 squared, which is a constant exponential t over 2. So we use this to prove the following proposition associated to our operator. There exists a constant C1 to C4 such that we have this expression 3, that minus log t c v squared is bounded by the bilinear form plus constant multiplied by v in L2 mu. And we have the expression 14, which is a Nash type inequality. So to prove 13, we apply the lower estimate of psi and Young inequality. To prove 14, by density, it's sufficient to take V in space of test function and use some order and Sobolev inequality. We obtain that. We obtain this is exactly to this Sobolev inequality and Holder inequality and Sobolev inequality. And by 14, we have that the gradient is exactly HVB minus U, so we can get 14. Now we have the main result here that under our condition, then the K mu associated to the operator H mu satisfy the following bound, where T is our transformation, which is equal to eta psi. To prove this, we need this lemma, Rosen lemma, tell us, assume that there are constant A1 and A2 such that we have the following bound for some n bigger strictly to 2, and G in L n over 2, and F in L2, then this inequality is true. So hold for some gamma epsilon and epsilon positive for any F in L2. Then we have that log Sobolev inequality, F square log U satisfy this estimate. So we use this. We have the following corollary. Let us assume that some condition on Rosen lemma. Then we have this exactly. We have the following bound of F square log F psi square, where psi is our ground state, where beta epsilon is defined by this quantity. And to prove our theorem, it's following previous proposition, and F in bigger or equal to 0 in L2, such that we have F in L2 with this weight, T, our transformation of psi square mu. We have the following bound, and then we apply weight log Sobolev inequality. We can compute this quantity. We use ultra contractivity and can be characterized by ultra contractivity can be characterized by log Sobolev inequality and ultra contractivity semigroup, and can be given by an integral Kernel. And the results follow now by taking into account that our kernel in the weight space satisfy this one, and to get our results is just we replace K mu by this one. Where is it? No, by this one, eta x, our kernel, eta y minus 1 plus y power alpha. So we get our results. To have better result, our result is sharp in space of variable in X, because we have this proposition. This proposition tells us that the estimate of a kernel is sharp, and in the case where B, the coefficient of the drift term bigger to 2 minus n, we can get better estimate in small time. So we have, so to get our result is just to replace the kernel by eta multiplied by k by eta, etc. So I think I have more time. I don't know what I want to explain.
You have 5 minutes.
5 minutes. Okay, so I will return to Okay, maybe I stop here. And maybe we can discuss question about if you have any questions. Just so here. Thank you.
Okay. Many thanks for your very technical